Hello, welcome to the second video in a three-part video series on how computers save data. If you haven't already seen it, the first video in the series is here, and we do a brief introduction on the topic. We talk a little bit about the analog world around us and how a computer has to digitize it and save it in discrete values. And then we also talk a little bit specifically about how we store things like numbers and letters. This video is going to explore how we retain sound, images, and video, and then we're going to wrap this series up with a video on how we do both lossy and lossless compression. Let's get started by looking at how we save audio. It's helpful to take a moment to explore just what audio is. When I'm speaking to you right now, the sound of my voice is being created because I'm breathing, and as I specifically mostly exhale air, my vocal cords are causing vibrations in the air at different frequencies to produce what we conceive of as using our hearing as different sounds. Those frequencies are just movement of the air at different wavelengths. So if I'm speaking at a high frequency, there's a lot of waves that are tightly knit, and if it's a lower frequency, the waves are more spread out. And how high or low that wave is, the volume is the amplitude, right? So if I'm talking softly, then the waves are not very high. And if I'm talking loudly, then the waves get high, right? So that's essentially, in a nutshell, what's happening here. And if we look at the mechanics of how we have speakers and microphones that collect and share this information, they basically just work because there is a paper or composite disc usually that picks up the movements in the air because the movements in the air cause it to move. And if it's a microphone, it's translating the noise in the environment into vibration that is then collected by an electromagnet that causes a electric pulse to go down a wire. And we can use the voltage changes that are caused by the changes in the speaker to record the frequency of the sound and the amplitude based on how much movement there is in this microphone. Now, on the converse side, when you're listening to music, your speakers are taking the same electrical signal that represents the frequency and amplitude, and they are translating into movement of the speaker, and that in turn moves the air around it, and you can hear it. Right? Now, once we involve a computer in this, everything we've talked to up until this point is considered analog. But once we involve a computer in this, we need to convert it to a digital representation. So to do this, we need to take the analog world and break it into discrete values. We have an example here where we're using 1 byte binary numbers to represent the amplitude. Now, we haven't shown all of the possibilities here, just a few of them, but since we have 1 byte, we know that our total range could be 256 in decimal. Now, if you haven't ever worked with binary and that's completely new, I have a video up here that will help you there. So definitely check that out. It would be helpful for this part. But this also means that we only have 256 values maybe in the positive space. If we want to have both positive and negative numbers, we need to have some kind of method to do that. Now here we're using complementary numbers. So the negative 16 that you see down here, this is actually a 2's complement of negative 16. And if you haven't seen that before, I have a video here that helps explain that as well. So what we're looking at here at the very top is the number 64 in binary, and if we remember our weights of 2, we have 1, 2, 4, 8, 16, 32, and 64, so having a 1 in the 64's place makes this the value 64. Down here we have a 48 because we have a 32 and a 16. Down here we have a 32 because we just have 132. And down here we have a 16 because we have 116. Obviously, our 0 here is represented by all zeros, and it is important to know that there are 16 possibilities in between this 0 and this 16, and I have not drawn all 16 lines to try to keep this chart more legible and understandable. We also go into negative space here, and we don't show all of the possibilities because remember, if we're using a complementary representation and dividing our positive and negative space roughly in half, we would have 127 positive values and 128 negative values, and that means that we would have a additional kind of doubling of what we see here above this. We would go up to 127 down here and negative 128 down here. So that gives us all of the discrete values that we can sample for this wave. If you try to sample a point in the wave, let's say that it's like dead center here, and it actually falls between -7 and -8. So, it's roughly equivalent to -7.5. We don't have a way to record that 0.5. The computer uses a process called analog to digital conversion, and it makes a decision on which is closest, and it picks either -7 or -8 depending on which one was closest. So when we do this conversion, we are not getting a perfect representation of the original value. We are getting an approximation, and the more that we increase the number of bits that we use to record that amplitude, the greater precision we have, right? If we add one more bit, now our range has jumped up from 256 to 512. And so 9-bit would give us 512. If we had 10-bit, we would have 1024. So every bit we add doubles that precision, but it means that we take up more space because every single sample we take requires that amount of bits to save it. Now the second dimension to this is how often we sample. So you can see here that we have these arrows here denoting when we sample. And what's important to know is that, this is going to be pretty often. If you only sample a few times a second, it's going to not sound like sound. It's going to be very choppy and not understandable. If you remember CDs, they're not quite that old, but if you remember CDs, they were considered to have, live quality sound, and they would sample for a CD at 44,100 times a second, or 44.1 kilohertz. So you can vary the amount of sampling, and you can vary the amount of precision that you use to record your amplitude, and you can basically use these numbers to multiply out to discover just how much disk space or bandwidth you're going to use and require to record a sound recording. It's also important to note that if you want stereo, of course, you're going to be doing this times 2. And if you have, say, Dolby surround sound, you're going to be adding additional channels, meaning that you're going to have the same exact thing for maybe 5 channels or 9 channels or however many channels that you decide you want to record. Now, what we've been discussing here is more or less as raw recording and as lossless as we can get in the digital world. Remember, it will never truly be lossless because, again, we're determining some amount of loss by deciding what our precision is on how we record the amplitude and how often we record the samples. And no matter how big we make those numbers, there will always be some imprecision there. There is no way to completely capture the analog world in the digital one. They are, by definition, that is just not possible. So what we want to do, though, is kind of capture it as well as we can to where there's no difference to the human ear that we can discern. But the problem is that this still makes pretty big files. So we don't typically use a raw recording like this. CDs, for example, were about 770 megabytes. Now, in today's world, that doesn't sound like a huge amount, but remember, that's just one CD. If we were still in the pre-cloud era where we all, now get our music online through a cloud service, and you had your own music libraries, you might have had hundreds of CDs in your collection, and if you multiply that out, it is a substantial amount of space. So the alternative was to start here, but then to further compress this information. Now we're going to talk more about compression, both lossless and lossy, in a dedicated video coming up, but I'm going to start the process by kind of talking about it a little bit as we go through both sound and images and video. So starting with sound, I'm only going to talk here about the predominant kind of format, which is MP3. There are, of course, others like OGG and FLAC and that kind of thing, but I'm going to stick with just MP3 because it's probably the most common and the best contrast of just the raw WAV file. So what happens with an MP3 file is we start with that idea of a raw WAV file, but we use this idea of psychoacoustic lossy compression to basically weed out the parts that hopefully humans can perceive or hear. So for example, there is a range of sounds that we are capable of hearing. And there are lots of frequencies outside of that range that we are not. So if the sound recording picked up those out of range frequencies, there's really no good reason to keep them because nobody can really hear them. At least most people can. There's also a lot of sounds that happen that the changes happen too quickly for our ears to pick up. We actually need a discrete amount of time to kind of occur before our ears really pick up the differences in a frequency. So there's a lot more to this, but suffice to say, there's a lot of musical information, so to speak, that we can kind of throw away safely, and people can't really tell the difference. There's also ways that we can compress that doesn't cause loss, and we're going to talk about those algorithms in the third video specifically. But let's just say for now, using these two methods, we can get the size of these files down considerably. So I mentioned on the last slide that a CD was, I think, 770 megabytes in around that size. And let's just, for a round number, although they very commonly had 12 or 14 songs, let's just say it has 10 songs on it. So that gives us a size per song of about 77 megabytes. Well, that same size song could easily be a 4 or 5 megabit MP3 file using these compression techniques. So it was a format that allows us to significantly drop the size of the file for hopefully not losing any perceivable loss in quality. I want to take a look now at visual data. So there's two approaches that we can take to store visual data. And I'm going to focus first on images and then we'll talk about video, although really video is just multiple images and we'll get to that in a moment. But the two approaches that we have are bitmap or raster images or vector or object images. So a bitmap or a raster image is the more common one, and that's the one that's built out of pixels. It's probably a term that you've heard before. Pixels are individual spaces on your screen that show some kind of color. So you could have 10 by 10 pixel screen, which would give you 100 total pixels on that screen because you have 10 across in a horizontal fashion, 10 in a vertical fashion. And each of those pixels can show some number of colors. So we could keep it simple and say it's black and white, and they can only show one color, like black or white. We could say that we're going to represent it with 4 bits, and they can show 16 possible variations of color. So that could be a grayscale. Now, in modern world, we use many more bits than that, usually 24 bits to denote all the possible colors, and we'll talk more of that in a moment. But basically then what we're saying is that every single pixel on your screen uses some number of bits to denote its color. And we have some number of pixels on our screen. Commonly today we have HD screens, which are 1920 by 1080 pixels. We have 4K screens, which are much larger than that. I think they're 2880 pixels down and across. I forget the exact number, but it's over 4,000. So these can be pretty large, and we end up with millions of pixels on the screen. So that means that we have a lot of data to deal with here. Vector or object images we'll talk about more later, but they take a completely different approach. They are not tied to specific pixels. In fact, what they do is mathematically represent all of the images on the screen. Looking a little bit more in depth at Bitmap here, this is a very simple representation of a screen that is 22 pixels wide by 23 pixels high. And every single pixel on this is denoted by its kind of 0 or 1 value here. So we have a black and white image, and in this case we only need 1 bit per pixel. So we have 506 pixels on the screen, 22 times 23, which means that we need exactly 506 bits to retain the information about what is here. If there's a 0, it's a white pixel, and if there's a 1, it's a black pixel. And using this method, we can use 506 bits to show any image here, as long as it's black and white, and store it and show it back to the user. Now, obviously, if we want more color here, we need to add more bits per pixel. So here we have a full color image that is more in the modern space. This image was originally 6,000 by 4,000 pixels. This was taken with a 24 megapixel camera, so that's how it gets to its 24 million pixel resolution by multiplying out those two numbers. And it has a bit depth of 24 bits per pixel. So just to get a feel for just how big these images get, and again, we're not talking compression here, we're talking in a raw format, in an analog to digitally converted format. We have our 24 million pixels multiplied by 24 bits, which gives us 576 million bits, which usually we talk in megabytes. So it's important to remember the difference there. If you're doing your math in bits, to get to megabytes, you have to divide it by 8 to kind of get to that number. So if you take 576 megabit and divide it by 8, you get to 72 megabytes. So again, this is without compression. Now you're probably aware, if you've ever looked at like a file like a JPEG or something, images even at this size of 6,000 by 4,000 pixels are much smaller. So that should give you a hint of just how much compression is doing. But again, we're going to talk much more about that in the future. Some specific bitmap formats I want to touch on. We have GIF and PNG or PNG. These are lossless. Now, what that means is, as we'll talk more about when we get to compression, there's two types of compression, lossless and lossy. Lossless means that we don't lose any information. Now, granted, doing the analog to digital conversion, we're always going to lose information, right? We can't take perfect and make it discrete without losing something. But when we say lossless, what we're specifically saying is once we've made that transition, once the analog world has been captured digitally, we don't further the damage. We might find creative ways to compress and save space, but we don't do it in a way in which we throw out any information. So when we were talking earlier about the audio files, and I said some frequencies are outside the range of the human ear, that would be considered a lossy compression approach, because even though humans can't hear it, we are throwing away information that we once had. A lossless approach does not do that. So GIFs and PNGs do not throw away any data within the image, they keep it all. Now, a GIF is unfortunately pretty limited in colors. It only had 8-bit color, which means that it had a 256 per pixel color spectrum. Now, if you've ever seen a GIF, this is quite evident when you look at it. It almost has like that 8-bit old school video game feel to it. Now, the reason GIFs though are still kicking is because they have animations. There was a kind of bonus in the GIF format where you could put multiple images within the same image. It had this kind of background mechanism where you could position different images, but what people commonly do is just position them over each other, and then you can actually set a time in which each one is shown at the top. Now, PNG was kind of seen as a successor to GIF, as a lossless approach, and it supports much more color. So 48-bit color is a lot, way more than is commonly used, but it means that PNGs are capable of that combined with their lossless approach of being very, very precise in their format. It also means that they can tend to be a little bit larger, sometimes a lot larger. Now, PNGs did not unfortunately bring the animations forward either. That's something that solely stayed with the GIFs, which is why you only see those in those kind of older, less colorful images with the animations. JPEG, on the other hand, is a format that actually has lossy compression. So just like we discussed with audio, with the frequencies that are outside the human hearing, lossy compression with images means that we might decide to kind of throw out little bits of data that maybe there's not enough variation between two colors in the grass, and we just kind of all make it a little bit green together, the same pixel, and because of that, we can then repeat that pixel or not save that pixel. So there's a whole bunch of techniques there that we'll talk a little bit more about later, but that's the idea of lossy. We're not saving all of the information. We're disregarding some of it. This means that we're going to have much smaller file sizes. JPEG, though, has proven that it can do this lossy compression in ways that, again, we don't really perceive. So it has become quite popular as a photography format, since the photographs still look really crisp and sharp and appear to the human eye to not really be degraded in any substantial manner, but they offer a vast amount of file size savings where, if you're saving hundreds, thousands, even maybe millions of images, and especially later when we get into video, this becomes super important, then, the trade-off is well worth it. Now let's talk a little bit about vector. Sometimes these are also called object images. So if you remember when we said there was two types of images, we said there was bitmap, which we just discussed, and then there's vector. Vector, we said, was mathematically focused. So we're literally taking here and using geometry to figure out formulas to draw. So if you imagine a circle, for example, we all know that a circle has a center point that we can identify in two-dimensional space with x and y coordinates, and it has a radius, right? And if we know those two things, we can draw a circle. If we have a straight line, we just need to know its end point in space and its start point, xy to 1 to xy 2. And we can draw a line. We could also do the same thing with a start point and a length and a direction, right? So there's all kinds of ways that we can apply mathematics to draw pictures. Now, the interesting part about this is that it actually means that these pictures can scale to any size, because remember, it's just math. So I can actually create a vector image and display it in a 64 by 64 tiny little image like an icon. And I can take that same image and display it as big as my screen in 4K. Or I could put it on the side of a building in a billion pixel by billion pixel imaginary screen, and there would be no loss of quality because the math would just scale. So whatever size it was scaled in that little icon, it would just proportionally scale to the correct size when it's on the side of the building in the magical, hypothetical billion pixel by billion pixel screen. In some ways, vector scaling is almost analog in nature because we're using math to recreate this idea that something can be in fact kind of infinite in how we treat it. Now, the flip side to this, though, is it's very hard to represent all types of imagery in mathematics. Now, that doesn't mean that this can't improve, but currently we do not have the wherewithal to do this with, say, a picture of a field and flowers and that kind of stuff. When you see a vector image, it's usually very identifiable. It either looks like what we're looking at here, this kind of almost like modern clip art feel, or it looks a little bit like this because movies like Shrek and a lot of the modern kind of cartoons were in fact made as vector images. Now that we've discussed images, it's a good time to kick over into video. And as I mentioned before, video is pretty straightforward. Video is just many, many, many bitmap images. So we basically take a bitmap image and then we say how many frames do you want to show per second, and we collect that many per second, and then we multiply that by minute and hour and so on. And just to get a feel for just how crazy this can get, in the modern world, we kind of think 4K is now, normal. It took a while to get here, but we're here, and we kind of expect all of our favorite shows and movies to be in 4K. So if we look at uncompressed numbers, now, of course, these are not the real numbers that you see. We'll talk more about that in the compression session, but I want to start here just to kind of give the gravity of the situation and why the compression is so important. If we look at 4K uncompressed, our resolution is 3840 by 2160, which gives us over 8 million pixels. It gives us 8.294 million pixels. Now remember, if we multiply that by 24-bit color, so every single one of those 8 million pixels has 24 bits representing it, that gives us effectively 200 million bits per image, 199 million. But remember, we like to talk in megabytes or gigabytes or whatever it is. So we have to take the bit number and divide it by 8 to get to bytes, which gives us 24,883,000 megabytes. So roughly 25 megabytes per frame. Now, I didn't use the rough numbers, by the way, in the calculations, just to kind of lay it out easier to look at. Now, if we imagine 30 frames per second, now this does vary, of course. Movies were 24 frames. 30 frames, I think, is pretty standard for kind of standard video, but it depends, on how you set up cameras and things like that. But remember, too, there's also a lot of refresh rates now that are a lot faster than that, 60, 120. I mean, there's even video games at 240. It's a little bit of a different thing, but just to kind of put this into perspective, 30 frames is not a hard limit at the top. This is yet another dial, so to speak, that we can tune as far as how much we want as far as quality and how much we're willing to give up as far as size. But let's use the kind of standard 30 frames a second. So if we multiply our last number by 30, for every second of video, we're looking at 746.5 megabytes. That is 3/4 of a gigabyte per second of 4K video. Now, if you take that and you multiply that out by 60, that means that per minute, we're at 45 gigabytes per minute, just for 1 minute of uncompressed 4K video. And in the hour, if we were to watch 1 hour, that would be 2.687 terabytes, almost close as whatever to 3 terabytes. So that is larger than most hard drives today. That is larger than the majority of SSD drives, and especially SSD drives in desktops and laptops today. And that's for 1 hour of video. You could have 1 hour of video, you could have like a half hour of video would fill up most hard drives at this rate. Now, it's not just the hard drives that are the breaking point here. It's actually the network bandwidth. Because how do we get video nowadays? We stream it, right? We stream it over services like Netflix and Hulu and YouTube, right? You're streaming me right now. I recorded this in 4K. So we would literally break the internet so badly if we all tried to stream this uncompressed. It would just be a problem that would have prevented anything even close to 4K from even happening for a long time. But that is why we need the next part of this, which is compression. I want to point out that as I went through this video, I had a few references, so I've linked them here. I'll also have them in the description below. And thank you for watching. If you haven't seen my channel before, please check it out. We're trying to create a repository of computer science knowledge and also just help people do everything from learn to code to learn the computer science fundamentals better and have a great forum to come back to anytime that they want. Please do like and subscribe. We appreciate it, and have a great day.